Now we are coming to a harder issue. We are going to study the joint and the marginal probability density functions of continuous random variables. Remember now, so far we have studied the discrete random variables. The discrete random variables were easy because of this tabulation. In this tabulated format, you can do everything by writing them in this table, and you can calculate the marginal probability mass functions and answer related questions related to marginal probabilities. However, for continuous random variables, the problem is not going to be that practical. Okay? Now, imagine, so when we were modeling a continuous random variable, if you remember, we were using a probability density function, right? And we were saying that there is a probability density function, and we were calculating the area under the probability density function in an interval to calculate the probability of that random variable to be in that interval. Okay? So that was our procedure. We were integrating the probability density function within an interval to calculate that interval's probability. Now this time, because we are studying with two random variables, this time we are going to have a joint probability density function, and that density function is going to be again a non-negative function, just like the marginal probability density functions that belong to a single random variable. And this time it is going to be denoted as fxy, which means this probability density function belongs to two random variables at the same time, and it is going to have two input values as well. Okay, so this is going to be the density function. Now, how do we use the joint probability density function in calculating probabilities? For example, if somebody asks you the probability of the first random variable x to be less than or equal to a, and the second random variable y to be less than or equal to b at the same time, so this means this comma means intersection, if you remember. So that probability means what? It is the joint cumulative distribution function at a and b, because both of these inequalities are given in the form of less than or equal to. Now, how do you compute such a probability with joint probability density function? You take a double integral, my friends. Let's just say the interior integral belongs to x operator and the outer integral. So this is the inner integral. This is the outer integral operator. The inner integral operator is x, which means we are supposed to take the inner integral from minus infinity to a, because x is supposed to take values less than or equal to a. Similarly, the outer integral operator is y, which means the outer integral boundaries should be from minus infinity to b, because y is supposed to take values less than or equal to b here. And inside this double integral, we write the joint probability density function. So exactly what is happening here? Remember now, this is a joint probability density function that belongs to two random variables. Actually, that belongs to two random variables. So it's a function of two values, two variables, which means over one axis, we have the x value, over another axis, we have the y value, and over a third axis, we have the joint probability density function. So this function is actually a three-dimensional function. Therefore, and it is non-negative, therefore, under this function, there will be a certain volume, okay? Unlikely to a single-dimensional probability density function, we are not going to have an area under that function. Under this function, we are going to have a volume, because it is three-dimensional. And that volume should be equal to 1. Should be equal to 1. So this is the golden rule for two-dimensional or bivariate joint probability density functions. So remember, now in the tabulated format for discrete random variables, as you can see, the summation of joint probability mass values is equal to 1. Just like that, if we take a double integral of a joint probability density function, in that case, we are calculating the total volume under that function, and the total volume under that function should be equal to 1. And that integral, the above integral here, is showing me the total volume under the function for x values that are less than or equal to a and y values that are less than or equal to b. So this is calculating the total volume only in that region, okay? However, we need to run a double integral because we are calculating a volume under that function, not just an area. Okay, so the total volume, so joint probability density functions, which are defined for two random variables, are three-dimensional functions which are non-negative, and also the total volume under these joint probability density functions should be equal to 1. And another thing, if we have a joint cumulative distribution function, if we take two derivatives, first with respect to x and then respect to y, then we are going to get the joint PDF. Okay, so the second derivative, first with respect to one variable and secondly with respect to other variable, then you are going to get the joint PDF if you take the second derivative of the joint CDF. My friends, it doesn't matter in which order if you take the derivative. Okay, if you take the first derivative with respect to x first, then with respect to y, or vice versa, it doesn't matter, still you are going to get the same function. Similarly here, when you are calculating that probability, you can basically interchange, swap the order of integrals. So you can take the integral operator dx to the outside, and similarly, these integral boundaries can be taken outside here, okay? So if you swap the integral operators, you also need to swap the boundaries as well. Be careful. But I mean, in which order you take the integral, it does not matter. Now, just like in the discrete counterpart, discrete case, we can determine the marginal probability density functions that belong to x only and that belong to y only by using the joint probability density function. The joint probability density function keeps a lot of information about both random variables. So it does not just keep information on the dependent structure, we can also derive the marginal probability density functions. How we can do that? Now, in the discrete case, we were doing what, if you remember? In order to compute the marginal probability mass function of x, we were running a summation of the joint probability mass values over y, over changing values of y. And similarly, for the marginal probability mass function of y, we were running the summation of the joint probability mass values over variable x. So we are exactly going to do the same in a similar fashion. If in a marginal, if you are interested in the marginal probability density function of x, then you are going to integrate the joint PDF over integral operator y from minus infinity to plus infinity. Similarly, if you are interested in the marginal PDF of y, then you are going to integrate the joint probability density function over variable x. So why we are doing this? Because if you are interested in the individual PDF of x, then the other variable should be eliminated from that equation. It should be eliminated from that equation. So what we are exactly doing here is this. So this function is a three-dimensional function. It is a three-dimensional function. And if I am interested in the marginal PDF of x, I am basically squeezing that three-dimensional function into one dimension by integrating over y. So I am squeezing the function over y-axis, okay? And that squeeze is going to bring me a two-dimensional function, which is a function of x only. Similarly, if you want to get the marginal PDF of y, which is one-dimensional, two-dimensional, in that case, you need to squeeze this three-dimensional function over axis of x, so it is going to get out of the equation, okay? So please do not confuse this. Now, let's just say you have determined the marginal PDF of x and marginal PDF of y. What can you do with these? You can calculate the respective expected values or respective variances, or you can also calculate the marginal cumulative distribution functions as well. Once you compute the marginal probability density function for x, if somebody asks you the marginal CDF of X, then you are going to integrate the marginal PDF of X from -infinity to X by changing the integral operator to T. And you can also compute the marginal CDF of X and marginal CDF of Y. Okay? So actually we are combining everything that we have learned so far with the joint probability representations.